Okay, we're going to continue on here, chapter 7. Last time we talked about stuff. We talked about moles. That's what we talked about. That sounds familiar. So we talked about balancing equations as well. And as we talked about in types of reactions, remember that you always want to make sure two things. You want to make sure that your equation is always balanced. So even if they give you the equation, you do want to take a moment to make sure that it is balanced. Pretty much everything that you do in chemistry, as we talked about, you do need a balanced equation. Again, if you do see some numbers in it, it is probably going to be balanced. But if you don't see numbers, you really should take a pretty good look at it. And even if you do see numbers, you should also take a look. We talked about two different types of reactions as well, ways to classify them. Remember that pretty much all types of reactions fall under one of these two sort of big categories of reactions. And that is redox reaction or double displacement. And a redox reaction really takes care of electrons being transferred. And when you do have a redox reaction, there's two things that always occur basically together. There's something that gets oxidized. And somebody that gets oxidized is basically losing electrons. And there's something that gets reduced or goes through reduction. And those are guys that will gain electrons. So we talked a couple of different ways you can remember that. The oil rig, the Leo the Lion says grr. But remember, you can look at what is really the oxidation number if you want to think about it like the charge. And when things do lose electrons, as they go from reactant side to the product side, they become more positive. And that means that they are going through oxidation. And if you follow sort of the oxidation state or the charge from left to right of the arrow, and it becomes kind of more negative or moving in this direction, it is going through reduction. So that's a very simple way that you can basically figure out, what is being oxidized, what is being reduced. Just simply which way is moving. Is it moving in a more positive direction? Is it moving more negative direction? And you can look at the chart. So remember that if you do have anything that is by itself, not combined, just like an element by itself, basically, it will always sort of have an oxidation state or a charge basically of 0. And then is when those ionic guys get together, a metal and non-metal, that's when they have the charges that we associate with them. Now, under this sort of classification of reactions, we have more specific sort of classifications. We have our synthesis reaction, where two things make one thing. We have the opposite of that, which is the decomposition, where one thing breaks apart into two or more things. We also have the single replacement reaction that occurs. And we also have the sort of combustion reaction that occurs. So those are, again, sort of more specific classifications of reactions. Ultimately, though, what is still happening is a redox reaction. Electrons are being transferred in that process, but you can classify it that way as well. In a double displacement reaction, you have basically two ionic compounds to start with, and that's always how you could sort of recognize it. And always in a double displacement reaction, what happens is basically the two positive ions switch partners. And as they switch partners, they will make two new ionic compounds on the product side there. And in one of these cases, perhaps one of these guys will make a solid. And that type of reaction is what is referred to as a precipitation reaction. So a precipitation reaction is really a double displacement reaction where one of the products makes a solid. The other sort of thing that could happen is maybe we react an acid and a base together. And when you react an acid and a base, neutralization reactions, they basically will form water. So you basically get a salt and water is what is formed as a result of an acid-base reaction. A salt is just an ionic compound. And really, those sort of three things are really the three reasons why any reaction takes place. Either there's an electron transfer, there's some type of solid that's formed, or you basically form water. Those are basically, you can cut it down to the heart of the matter. Those are really the three things that occur and why a reaction does occur. As we also saw, you can definitely classify the same reaction in multiple ways depending on what you're looking at. So I think the one we talked about there was like magnesium and oxygen, making a little magnesium oxide. And definitely this is two things that make one thing, which means you could classify it as a synthesis or combination reaction. This is also a redox reaction, which you could classify as well as the charges change, with the magnesium being oxidized, the oxygen being reduced. And lastly, because it frankly has O2 in it, you could classify it as a combustion reaction. So you could actually classify the same reaction in a few different ways depending on what you're looking at. Any questions on any of that stuff there? At that point, we moved on and talked about moles, which was mentioned earlier. And remember, in chemistry, the mole, which is abbreviated as MOL, it does represent a certain amount of something, which is Avogadro's number, 6.022 times 10 to the 23. And these could be atoms. They also could be molecules, most common. And that really is used as a conversion factor, as we did in a couple of examples, to really go between those units. So if you need to go between moles to atoms or molecules or backwards, that is Avogadro's number is what you should use to do that. Remember that you should not use Avogadro's number unless it does say something like that, like molecules, atoms. That's mentioned somewhere in the problem. Either you have a number that's in those units, or you're asked to basically find a number with one of those units. Remember, if it doesn't mention any of those things, then you really should leave Avogadro's number on the side there and you shouldn't use it. The other important thing, again, is that MOL is the abbreviation for moles, not molecules, which again is a very common mistake that a lot of people will make, bless you. Now, the other really kind of main conversion that we use a lot in chemistry is molar mass. And molar mass comes from the periodic table. It again is those units or numbers that we see on the bottom, and we use it in terms of grams per mole, and that is the units of molar mass. The number always stays with the grams part, and it's always 1 mole of what we got going on there. So that is a really important conversion. That is the conversion that we use to go from moles to grams and backwards, grams to moles. And that definitely is in chemistry pretty much, I would say, even more than Avogadro's number use is one that you use a lot. So that mole to grams, grams to mole conversion, very important, always taken from the periodic table. And as we talked about, basically it's about 4 significant figures is usually what you pull off the periodic table in terms of how many numbers. And that is also usually how far you would calculate the molar mass if you calculated for it. You could calculate the molar mass for anything. So you could do it for just one element by itself, and that would just be the number on the periodic table. And as we saw in a couple of examples, you can also do it for like molecules or compounds. You just add up all the parts. So you add up all the parts that are there, and that's how many grams there would be per mole. It's important for molar mass that it is always 1 mole. So whenever you need to calculate the molar mass for something, regardless if it's in an equation, there's a number in front of it, it doesn't matter. You should only take the formula, and that's the only thing that you should use to calculate the molar mass. So just the formula is the only thing you should do. So again, if you had something like water, and even if we had water, say in an equation, and there was like a 2 in front of it, it doesn't matter. If we were just looking for the molar mass of water, we would just use the formula. And as we might have done last time, 2 times 1.008 grams per mole for the hydrogen, plus 16 grams per mole for the oxygen. And that means the molar mass here of water would be something like 18.02 grams per mole. So again, always important. And that's also a very common mistake that people make. They see it in an equation and they start using the number that's in the equation, just the formula to calculate the molar mass. Any questions on any of that there? Okay, so we did some examples, obviously, of converting grams to moles, moles to grams, also atoms and molecules. I did want to talk about another sort of calculation like that you might sometimes come across. So why don't we use something I think we use as an example as well. Let's just say we had 32.6 grams of C2H6O, and we wanted to know how many grams of hydrogen does it contain? So in this particular problem here, we're actually not interested in the entire compound there, the C2H6O. We're actually just interested in the hydrogen part. So we do need a way to kind of go from the whole thing to just the hydrogen part. And the way that we could actually do that is we could actually get some conversions that come just actually directly from the formula itself. So when we look at these numbers that are on the bottom, and obviously that's a 1 there if there's no number written, we could assume that these are the moles of each of these things. So we could actually use the formula itself as a conversion factor that will allow us to go from the whole thing to just one of the elements that are involved. So for example, from this actual formula, we could say 1 mole of C2H6O has 2 moles of carbon. And again, that 2 is obviously the 2 that we see in the formula. We could also say for 1 mole of the entire thing here, how many moles of hydrogen would it have then? It would be 6. And again, it is the number that we see here, 6 moles of hydrogen. And we could also say in 1 mole of the entire thing there, it would have 1 mole of oxygen, which obviously would be no number that is written there. So these are really like equalities. They're sort of mole to mole equalities. And we could write 2 conversion factors for each of them, just like any other sort of equality that we dealt with. We could say 2 moles of carbon up on top and 1 mole of the whole thing on the bottom, or you could reverse it. So that is really what we could use to go from the whole thing to the individual element, which is hydrogen in this case. In order to use that, though, we obviously do need to convert our grams of the whole thing into moles so that all the units cancel out correctly. So that would be the first thing that we would want to do. We would want to convert the grams of the entire thing into moles. I think we calculated the molar mass the other day. I want to say 48 and change. It kind of has that number in my head, I think. So if we calculated the molar mass from the periodic table like we did the other day, 4607, I believe, is what we got from the periodic table. And that is the molar mass of the entire thing here. All right, so the first step that we would do is we would take 32.6 grams of the entire thing. We would convert it into moles just like we were doing the other day here. We would put the grams on the bottom, 4607 grams per mole of C2H6O. At this point, if I stop the calculation, I am in moles of the entire thing. And that is good because I do want to get to hydrogen. So that's going to allow me to use the conversion factor that I see here, which is right here, that comes from the actual formula. And I'm going to use that just like dimensional analysis. So I want to get rid of the whole thing. So I'm going to put 1 mole of the whole thing on the bottom. And we're going to do 6 moles of hydrogen. So that step there, using the formula as a conversion factor, is going to allow us to get rid of the whole thing and now end up with just the moles of hydrogen. That is close to what I want, right? I do want to end up, though, in grams. So I need to go from moles of hydrogen to grams. I should use what to do that? What is the conversion between moles to grams? It is the molar mass from the periodic table. At this point, though, I need the molar mass of just hydrogen, yeah, because we're no longer dealing with the whole thing. So we would go to the periodic table there, we would look it up, and we would see hydrogen is 1.008 grams per mole. And that would be the last step here that we would do. Once again, we want moles to cancel, so we'll put that on the bottom. 1.008 grams of hydrogen up on top. The moles will cancel. Now we're going to multiply across the top there, which would give us 32.6 times 6 times 1.008 divided by 4607 here. That's going to give us about 4.28 grams of hydrogen is present. So that is sometimes a sort of problem that you might come across where, again, you're not necessarily interested in the entire compound that's given to you, but just maybe one of the elements that are there. And again, you can use the formula as a conversion factor. Questions on that there? All right, so why don't you try one here? Let's see what you get. We'll use the same one so we don't have to calculate the molar mass too many times here. So we'll do the same. We'll do 32. I will change it up here. We'll do 39.5 grams of C2H6O. In this case, we want to know how many carbon atoms are there. All right, so give it a go, see what you come up with. Okay, let's take a look. So a couple of things here. What we obviously see, we're looking for just carbon. So as we were just talking about, we're going to, again, need to use our formula to take us from the whole thing to just carbon. So we do know from the formula, we could say that there is 1 mole of the entire thing will give us 2 moles of just the carbon. And again, that is the little number there on the bottom. We also know we will have to take our grams of the whole thing into moles to do that. We also see another important word, which is atoms, which means somewhere along the way, our good friend Avogadro, right, needs to come into play. And we're going to actually use at the end here to go from moles to atoms. So we'll start this one very similar to what we did on the last example. And I'm just going to steal the number there. That was 4607. We once again would need to go to the periodic table to get the molar mass, so it should be the same number. So we will take our grams of the entire thing here. We will convert it into moles, once again using our molar mass with the grams on the bottom so that they cancel. And now we're at moles of the entire thing. So once again here, we're going to use the formula as a conversion factor to go from the entire thing, which should go on the bottom here. So 1 mole of our entire thing will give us 2 moles of carbon. So the moles of the entire thing do cancel. And here's the difference. Obviously, in the last example, we were looking for grams, so we used the molar mass last time. But here we are looking for atoms, so we actually do not need the molar mass in this case for carbon. So we would use Avogadro's number. Again, that is the conversion factor to go from moles to atoms, or atoms to moles, back and forth, or even to molecules as well. So in this case, we do want the moles to cancel, which means on the bottom should go 1 mole, and Avogadro's number should go up on top here. And that would be atoms of carbon. The moles of carbon would cancel, and that would give us our atoms that we're looking for. Once again, here, we're going to go through and multiply everybody here up on top. And then we pretty much just need to divide there by the first guy. Remember, at the end of the multiplication, you probably hit equals. So make sure you do that. Also, make sure you use your exponent button with Avogadro's number. So we'll hit equals there, and then we're going to divide it by 4607, also hit equals. And that is going to get us 1.03 times 10 to the 24, and these would be atoms of just carbon in this case. So that's sort of a variation on your grams to moles, moles to grams, where we kind of focus in on just one of the elements. Any question on that calculation, where the numbers came from, or anything like that? Yeah. Did I put 1 mole where? I'm sorry. Yeah, you can. You can put 1 mole. Yeah. Other questions? Questions on grams, moles, grams, Avogadro's number? Very good. Professionals, I like it. Yes. I don't know. All right. So what we're going to talk about now is actually putting together the 2 things we were just talking about in this chapter. We're going to put together basically equations, and we're going to put together grams and moles, and we're going to do calculations from equations, which will basically tell us, for example, how much product we should make if we did this reaction, or if we know how much product we made, we can figure out how much reactants we started with. This is what is referred to as stoichiometry. So we're going to talk about stoichiometry, which is really calculations from the actual balanced equation. So I can't emphasize it enough, as we were talking about balancing equations and stuff like that. You must have a balanced equation, which is definitely going to be wrong. So always make sure that thing is balanced. So let's talk a little bit about it. From an actual balanced equation, we could actually come up with some sort of conversion factors that we could use in calculations. And a lot of them are based off of the coefficients. So for example, if we look at the coefficients here, which obviously that would be a 1, we could say that there are 2 molecules of H2 react with 1 molecule of O2 to give us 2 molecules of H2O. The sort of conversion or relationship that we use the most is really the next one. We could also say that there are 2 moles of hydrogen react with 1 mole of oxygen to give us 2 moles of H2O. That is the relationship that we use in stoichiometry and these type of calculations. It's sometimes referred to as the mole-to-mole relationship. The last one is just a conservation of mass, and that's really the reason why we balance equations, right? So if we have 2 hydrogens or 4 hydrogens on the left, we have 4 hydrogens on the right, and each hydrogen is 1.008. So we have that conservation of mass that we should have. Remember that we never lose any elements along the way in a chemical reaction. They just get rearranged. So we break all the bonds and they all kind of reassemble on the other side in new substances. So this mole-to-mole relationship is really important, and we use them really as conversion factors. So sometimes people get really kind of freaked out about stoichiometry, but it really is nothing more than just a conversion factor. And the difference is the table, the actual chemical equation. Kind of similar to what we did with the actual formula, where we could use it as a conversion factor. That's basically what stoichiometry is, equation, and come up with some relationships that will allow us to go from one thing in the reaction to something else. And the reason that is in most stoichiometry problems, they will give you some information about somebody in the equation, but you're actually interested in somebody else. So you need a way to kind of go from one substance to the next. And that's really where the stoichiometry comes into play. Now, in terms of units, and for us, pretty much the units are going to be probably grams to moles, moles to grams. But they can be other units. Reactants can be liters, they could be molarity and stuff like that. But for us, we will pretty much stick to these two are going to be really the 2 units that we will see the most in stoichiometry. With that being said, this is why it's important what we were just talking about as well. That conversion factor to go from grams to moles and backwards. Again, that is your molar mass, which is your grams per mole, and that is from the periodic table. So that is like a super important thing. Outside of balancing the equation, that is like the most important conversion for stoichiometry problems, because very typically what you do at the beginning is you take something from grams to moles, and at the end, a lot of times in the calculation, you take it from moles back to grams. So going both ways is very commonly used in these calculations. If you just think about it logically, right, when you're in, say, the laboratory, when you go to the balance, it's in grams, right? So those are important sort of units that we oftentimes want to get answers in. So how do we go about doing this? The mole method is based on that idea, what we just talked about. It is nothing more than just the coefficient in the balance equation. There's no calculation in terms of how do I get that relationship. It is just simply that coefficient that you do see in the balance equation. So here are some common steps that you want to follow when you're working stoichiometry problems. And there's a couple extra steps on this chart here that you probably won't come across too often. But you could come across a problem where they may give you everything in words, and you would want to turn those words into proper formulas. And that would be like your unbalanced equation. You then want to balance the equation. And once you do that, you pretty much want to take whatever they give you and convert it to moles. Again, it's because of the mole-to-mole relationship. You then want to go to the equation and find the mole-to-mole relationship and then do your calculations. So pretty much this book could boil down to 4 basic steps for a stoichiometry problem. Make sure that we have a balanced equation. Whatever they give you, just convert it to moles. Or convert it to grams and then to moles, however you need to do it. But basically grams to moles. You then go to the equation and find the mole to mole relationship from the balanced equation. And lastly, if you do all those steps correctly, which hopefully you will be sitting at moles at this point. So if you did it correctly, you should always be at moles at this point. And maybe they do want moles as the answer, then you put a box around it. But in a lot of cases, they want some other unit. So a lot of times you have to do one more conversion on the back end. And that a lot of times is usually moles to some other unit, like grams. And again, a lot of times you could use the molar mass. These are pretty much the 4 steps you should always follow. And you should always follow them in that order. And if something is done for you, you just go to the next step. You don't undo it. And that's a very common mistake that people make is they like, oh, wait, it's already in moles. Let me unconvert it and then reconvert it back to moles. So don't go backwards. So if something's already done, just go forward. And you pretty much can follow these same 4 steps and you'll always get to the right spot as long as you don't make any math mistakes, I suppose, in that case. All right, so let's talk a little bit how we could do all these steps, and we'll do some problems here in just a second. But first off, let's say we have a balanced equation. So this is a balanced equation. And from this one equation, we could come up with several different relationships. And it is all based off of the coefficients in this balanced equation. So it is all based off of those numbers. So we could say, for example, in this reaction, for every 2 moles of CO that we toss in there, we can also toss in 1 mole of O2. They're equal to each other. We could also say for every 2 moles of CO we toss into this equation, we get out 2 moles of CO2. And lastly, we could say for every 1 mole of O2 we toss in there, we get out 2 moles of CO2. These are what are referred to as being stoichiometrically equal to each other, and there is an equal sign. They are equal to each other in terms of that is what you got to toss into this reaction, proportion-wise, to get it to go. They are not equal to each other in terms of numbers. So obviously 2 does not equal 1, so they're not equal, and that is equal in terms of what you need to toss in there. So kind of like when you make cookies, right? You got to throw so much flour in, right? So much chocolate chips, you get a dozen cookies, or depending on how big you make them. But you get so many cookies out. So that is basically what we're talking about when we talk about stoichiometry and these things being related to each other. Again, they are not related to each other in terms of numbers being equal, but they're equal in terms of what you need to put in there to get this reaction basically to take place. But because these are essentially equalities, what that means is for every single equality that we got going on here, we could write 2 conversion factors that could help us in a problem. So for the top one here, we could write that there are 2 moles of CO over 1 mole of O2. We could also flip it around. For the middle one there, we could write 2 moles of CO over 2 moles of CO2, or we could flip it around, 2 moles CO2 up on top, 2 moles of CO on the bottom. And lastly, for the last one there, we could write 1 mole of O2 over 2 moles, bless you, of CO2, or 2 moles of CO2 over 1 mole of O2. So from this one balanced chemical equation, we actually have 6 available conversion factors that we could use in a problem. Will you use all 6 in one problem? The answer is no. You're just going to use 1. So you just need to pick the one that you need. And again, it's really just about conversions and getting rid of the units you don't want. So for example, let's say that we We'll use this guy since we have it up here as sort of an example. Let us say that we started, actually we produced, we'll do this, we produced 10.5 grams of CO2. And we want to know how many moles of O2 did we start with? Okay. So in this case, we know that we produced 10.5 grams of CO2, and we want to know how many moles of O2 we started with. So we're going to go through the 4 steps here to see how we could kind of put it into play. So once again here, step number 1 is to make sure you have a balanced equation. So that is obviously done for us. So step number 1 is good. We have a nice balanced equation. Step number 2 tells me whatever they gave me, I need to convert into moles. So the only piece of information that was given to me is, 10.5 grams of CO2. So to convert grams into moles, I need the molar mass from the periodic table, and this is of CO2. So that's what I would want to first perhaps calculate is CO2 from the periodic table. There's 12.01 grams per mole for carbon. And there are 2 oxygens, each at 16 grams per mole. And that's going to go 4401 grams per mole. I hope. I'll grab my calculator and confirm, but I hope so. That's going to be like a 32 and a 1201, is it? Yeah. All right. So the second step is exactly what I said. We're just going to take whatever they gave us. And by the way, if it wasn't in grams, I might have to do a couple conversions to get it to grams, whatever it may be. But you want to basically get it to grams and then go from grams to moles. So we're going to do step number 2 here, which is we're going to take our 10.5 grams of CO2. We're going to use the molar mass here of 4401 grams per mole of CO2. And we'll get an answer here since we're going through the steps. 10.5 divided by 4401. And I'm not going to round too much because I'm going to continue on with the calculation. So I'm going to go with 0.23858 moles of CO2. First off, any questions on that? So here's really where the stoichiometry comes into play. The problem I have is the only piece of information that I have is about what? It is about CO2, right? Ultimately, I want to figure out how many moles of O2. So this is the big stoichiometry move. I need a way to go from CO2 to O2. So I basically need a way to get to there. And that is where the stoichiometry comes into play. So earlier we did it, right? And we saw from the equation that for every 1 mole of O2, right, which is the coefficient in front of O2, we get 2 moles of CO2. That gave us 2 possible conversion factors. That gave me this conversion factor and that conversion factor. The one that I should use is this or that. I know you don't remember. Left or right should I use here? Which one's going to get rid of the CO2 and keep the CO or the O2? It is the one on the left. That's the one that's going to do it. I know you're pointing left, but it's my right, so I'll turn around so I'm with you. So that's the line on the left there. We'll do that. So that is really the third and big stoichiometry step, the one people freak out about. That is it right there. It's really just a conversion. So that is what we're going to do next. We're going to use our mole to mole relationship, right? So basically we converted to moles. We are going to use our mole to mole relationship. So continuing on, obviously, with the number that I had in the previous step there, I'm going to go 0.23858 moles of CO2. Once again, using the conversion factor here on the left, I'm going to go 2 moles of CO2 on the bottom and 1 mole of O2 on the top. And again, that comes from our balanced equation. Yeah, this is where that comes from. And that is going to do the conversion that I need. And that will get me 0.119 moles of O2 in this case. Wait, go this way. Any questions on that? Do I need to go any further? I don't. In this particular case, we actually don't need to do step number 4, which is convert these moles into some other unit, because that's actually the unit I want, right? So I should put a box on it, and now I'm happy in this case. If I did want grams, what would I have to do next? I would need to use the molar mass of O2 in this case, right? To convert it from moles of O2 to grams of O2. Any question on that? It is, you could trust me, I've done this once or twice. It is actually the same 4 steps over and over again. Just follow the 4 steps and it will lead you down the right path. What this really means in reality is if we did this reaction and we produced 10.5 grams of CO2, we had to toss in there basically 0.119 moles of O2, which, by the way, is about 3.8 grams of O2 would have been tossed into there. Yeah. So although we did not need to do it in this step, just to, again, finish it out, if we did go to grams, we would do the 4th step here, which, again, we did not need to do in this case, and that would be 32 grams per mole. And that would be like step number 4, if necessary. And that gave me whatever I just said there, 3.82 grams. And it really is, again, just those same 4 steps. Any questions on any of those steps? Yeah. Yeah. So, so let's take a look at one here. So you're asking how we got these? Is that what you're asking? Yeah. Okay. Yeah. So what I'll do actually is I'm going to just steal this page, I think. And we'll look at a different one just so you can see another one. How's that? Okay, so let's say we have this equation here, N2 plus H2 NH3. We'll do a little balancing there, like good chemists here. There we go. Okay, so obviously none of this works if it's not balanced. So again, I can't emphasize how important it is to make sure that your equation is balanced. So here's how we get the relationships. Once you have a balance, your work is done for stoichiometry. Pretty much at that point, it is simply just the coefficients in the balanced equation is where we get those relationships from. So for example, in this particular equation, we could say, and if there's nothing written there, it's assumed to be 1 like normal. That would be 1 mole of N2 needs to react with how many moles of H2? 3. Yeah. For every 1 mole of N2 I toss in there, how many moles of NH3 do I need? 2, which is, again, just the coefficient. There is no trickery here. There is no calculation. It is really just the number that's in front. For every 3 moles of H2 I pop in there, I need how many to come out? How many moles of NH3? 2. Again, just the number. There's nothing more to it than just the number in front. Yeah. Now, each of these are equalities, which means we could write 2 conversion factors for each. In this case, we could write 1 mole of N2 over 3 moles of H2. And that just comes from writing a conversion factor from this equality. The opposite conversion factor is really just the inverse of it, or the flip of it there. And 3 moles of H2, we get 1 mole of N2. For the second guy, we could say for 1 mole of N2, we get 2 moles of NH3, or 2 moles of NH3, we get 1 mole of N2, and this one, 3 moles of H2, 2 moles of NH3, or 2 moles of NH3, 3 moles of H2. So again, those are the 6 different conversion factors that you could get for this particular reaction. And again, each of those equalities are just based on the balance equation, which is why the balance equation always comes first. Yeah, and you got to make sure that it is balanced. Question on that? So if we look back at the one we just did here, and I'll put this back up in just a sec. So if we look back at this one, we see that there are 2 moles of CO, and that's the coefficient, gives us 1 mole of gives us 2 moles of CO2, which is the coefficient over here. And gives us, so it really is nothing more than just taking the coefficient that is written there. Yeah. There's basically only, in this particular reaction, because there's actually 3 things, there's 6 combinations basically that you can have some that has less combinations, and in reality you don't necessarily have to write all the conversion factors down, but these are all the ones that are available to you to use. And like I said, in most calculations you're just going to choose the one that you need to allow you to get to where you're looking for. 8, yeah. So pretty much for every coefficient, there may be even be more than that. So because each one could go to it. Yeah. So let's take a look at this one while we're here. Why don't you try one? Let's say we did. Let's say we did 5.6 grams of H2. How many grams of NH3 did we produce? All right, why don't you take a few minutes, follow those 4 steps. Once again, if something is done for you, just go ahead. I'll give you some numbers. H and N is that's all we need. So H from the periodic table, 1.008, and nitrogen from the periodic table, 1401. All right, so follow those 4 steps. Something's done for you, continue on. We're starting with grams of H2. We want to end up at grams of NH3. Okay, should we take a look? So I wrote up here the 4 steps that you should always follow in these type of problems. Obviously, in most cases, you'd be given the problem there and maybe the equation. So the first thing that we want to do is to make sure that we have a balanced equation, which obviously I did earlier. Obviously, if it was not, then you should probably do that. All right, so we do have a balanced equation. The next thing tells us that we should take whatever they gave us and basically convert them to moles. In this case, this is the only thing that they gave us. So that is what we want to convert to moles. And in this case, it's in grams to start with. So we're going to do our grams to mole conversion, which is the molar mass from the periodic table. In this case, we would need the molar mass of H2, and H2 is basically 2 hydrogens, not carbons, 2 hydrogens would be better. And that gives us a molar mass from the periodic table as 2.016 grams per mole. And that is the conversion factor that we're going to use to really do step number 2, which is take whatever they gave us and just convert it into moles. So step number 2, we're going to take what they gave us, 5.6 grams of H2, using the molar mass there from the periodic table. We will convert that into moles, which means grams need to go on the bottom and moles need to go up here, up on top. And that will give us 5.6 divided by 2.016. And if we get an answer here, we got something like 2.7778 moles of H2. Any questions so far? Yeah. You do. So once again, that's what we were talking about earlier. Yeah, so anything that involves molar mass, and it is a very common mistake that people will do, especially in these type of problems, is you want to use just the formula. The reason we don't want to use the 3 there, and then we're going to use the 3 again, is you're going to use the 3 too many times. Yeah, so anything involving molar mass, just simply take the formula out regardless of the number that's in the balanced equation. If you were asked what is the molar mass of H2, it should be this number, and it shouldn't be 3. I'll get to your question in just one second. It would not be times 3, because then it really wouldn't be the molar mass of H2. It would be based in this problem, right? So it has to be just based on the formula. Are you talking about the number 2.77? Yeah, so I would not round too much in these type of problems because usually you're only on step number 2. So you got step 3 and 4 usually to go. So there's still kind of more to the calculation at that point. So you don't have to start to write out the entire number, but maybe take a couple extra digits. It goes back to kind of what we were talking about earlier on when we were talking about just doing conversions. You don't want to round too much if you're going to take that number and kind of continue on with it. So try not to do too much rounding until kind of the end. And like normal, you can kind of clean it up at the end to the right number of digits. Yeah. Other questions? All right, so I got number 2 done, right? So now I'm ready to go number 3 on my list here, which is the big stoichiometry move. And once again, that comes from the balanced equation, and it's those coefficients, and we had it written out earlier. But in this case, you're just really looking for the 2 things you're interested in. One thing you're interested in is whatever they gave you, which is obviously this guy. And the other thing you're interested in is what you're trying to find, which is obviously this guy, right? And from that equation, as we saw earlier, the relationship that we're really going to be focusing in on is for every 3 moles of H2, we get out 2 moles of NH3, right? And that is just that's the stoichiometry relationship there. That gives us 2 conversion factors that we could use in this case. And if I can find where they're at, they're on the bottom here still, I think. So we have this conversion factor that we could get from that, and we also have that conversion factor there. In this case, since we are sitting at H2 and we want to end up at NH3, the one we should use is the one on the left or the one on the right? Yeah, you're right. You're right about that. That would be you're right, is the one that you should use. And that's going to get rid of the H2 and leave us with NH3. And that would be the 3rd step that we want to do. We're going to carry on with this number. And to go to the earlier question, that's really why we don't want to round too much at this point, because we're going to kind of continue on with the calculation. We're going to take 2.77, a lot of sevens there, 8 moles of H2. And this is the big stoichiometry step. Don't blink, you might miss it. But we're going to go with 3 moles of H2 and 2 moles of NH3. That is the step that's going to allow us to get rid of H2, which is what we're not interested in, and allow us to get over to NH3, which we are. So we're basically going to times it by 2 and divide by 3. Once again here, I'm not going to round too much because am I done with the calculation at this point? I am not. I'm close. I'm at moles of NH3 at this point, right? So the last thing that we want to do is we actually do need to do step number 4 here. We need to now go from moles, in this case, to grams, which is a very common sort of step that we have to do. In order to do that, I need the molar mass of what at this point? I need the molar mass of NH3 because that is where I'm sitting at, right? So again, you don't want to use the same molar mass. We're at NH3 at this point. So we are at NH3, which means we do need to go back to the periodic table to do that. And since we didn't use some of these conversions, I'm just going to get rid of them so I have somewhere to write. All right. So obviously at this point, we are at NH3. So using the molar mass from the periodic table for NH3, that is 1 nitrogen at 1401. And that is 3 hydrogens at 1.008. That's a 1703, I think. So that is 1703 grams per mole. So I'll come up here and do the last step. So step number 4 here, we're going to take our number from step number 3, and we're going to go 1.8519 moles of NH3. Using our molar mass, we want the grams actually up on top and the moles of NH3 on the bottom. Moles will cancel. We're going to times that by our 1.85 and some change. And that's going to give us 31.5 grams of NH3. And at this point, I will round because that's the end of the calculation at this point now. I rounded, by the way, to 3 significant figures because of what? The only number in this problem is Yeah, 3 significant figures, right? So that's why we ended there. Question? Well, you know. All right. Well, I just want to make sure you're paying attention, of course. You would be right. So we'll delete that out later on in the video there. It'll be fine in post editing. All right. So all right, dub over that. We want 2 significant figures because clearly that is 2 significant figures. Very odd. I went with 2. I usually don't. All right, so that will go with was that 31, 2? We would round up to 32 in that case. Yes. It is again. Hopefully, you can see the same 4 steps. Balanced equation, convert to moles, mole to mole relationship, and convert moles to some other unit. Question on any of that there? What's that? Yeah, we got a few more to go actually, so let's do it then. All right. All right. All right, let's take a look at some here. Let's do this one here. Lithium metal reacts with water to form hydrogen gas and lithium hydroxide. How many moles of hydrogen can be formed from the complete reaction of 5.32 moles of lithium with water? Follow the 4 steps, see where you get. When you put some numbers up there, that might be helpful for you. And this should be on your notes, this one. Lithium 6.941 on the periodic table. Hydrogen 1.008. Oxygen 16. All right, let's start with the equation first, then we'll let you continue on with the stoichiometry part. Lithium metal should be Li, yeah. Reacts with means plus water, which should be H2O. Forms means an arrow, yes. Hydrogen gas is, it is diatomic, it is H2, and lithium hydroxide is OH. There you go, pick it up from there, yeah. All right, let's see how we're doing here. So once again, what I did first off is I took all the words and I made sure I had the proper formulas down, but I still need to do step number 1, which is to balance it because it is not balanced. And if you balanced it, I feel like you should put a 2 there, maybe a 2 there, and maybe a 2 there. Could just be writing 2s. I'm not sure, but you should. So we have 2 lithiums on the left, 2 on the right. We got 4 hydrogens on the left. We have 2 hydrogens here plus 2 more here as this gets distributed, right? And then we also have 2 oxygens there and 2 oxygens there as well, right? So we are balanced. All right. So once again, I can't emphasize enough that if you do not balance the equation, you're kind of wasting your time because none of your rest of your calculations are going to be correct. So definitely if you see an equation like that where you do not see numbers, you should take a very hard look at it to make sure that it is balanced. And if not, make sure that you do balance it. So I'm going to check off number 1 there. That looks done. The next thing I want to do is convert whatever they gave me to moles. And in this case, this is the only piece of information they gave me. Do I need to do that? I do not because it's already in moles. Don't go backwards. So I just put a little check there. I'm halfway through the problem. I've just balanced the equation. So again, a common mistake, people like to undo it and then redo it. No need to do that because you're just kind of wasting your time. Yeah. So again, if something is done for you, just go on to the next step. Which means the next step is I want to go to the equation, right, and find the 2 things I'm interested in. And in this case, one thing I'm interested in is always whatever they gave me, which would be this guy, right? The other thing I'm interested in is what I'm looking to find, and I don't remember. I'm looking to find how many moles of hydrogen, which would be that guy right there. So that is really, in this case, the only relationship I care about, right, in this particular problem. And again, we could get the stoichiometry relationship by simply taking the numbers that are in front of each of those. And that means that for every 2 moles of lithium I toss in there, I'm going to get out 1 mole of H2. So that is the stoichiometry relationship. Again, if you want to, or if it helps you, you could write the 2 conversion factors that you could get from that. I could get 2 moles of lithium up on top, 1 mole of H2 on the bottom, or I could use it the opposite way, where H2 is up on top and 2 moles of lithium are on the bottom. Any questions on that there? How I got that relationship? All right, so I do need to do actually number 3 here, which is to use that relationship to move us from lithium to H2, which is what I'm looking for. So step number 3 here is going to be the 5.32 moles of lithium that was given to me. Using that relationship that we just got, we want to get rid of lithium, which means we are going to use the one here on the right, and that would be 2 moles of lithium is 1 mole of H2. That right there is the big stoichiometry move. That is going to get rid of moles of lithium. And now I'm at moles of hydrogen, which means I take 5.32 and divide it by 2. Gives me 2.66 moles of H2. That is step number 3. Do I need to do step number 4 in this case? I don't, because the units I'm looking for are moles of hydrogen. I put a pretty box around it. Yes. And maybe a happy face next to it. I don't know, any of those things. Yeah. 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 Yes. So I did that to show you that those are all the possible conversion factors you could get. And like I said, in most problems, you just need one. So like we did here, you can very much simplify it by just simply focusing on the one that you need. Yeah, in this particular problem, you didn't need to, but you could have had a different problem that had the same equation, where it maybe want to know how much LiOH you would have made, then you would have needed it. Yeah. You don't combine anything. Everything is separate in terms of stoichiometry, in terms of the relationship. It is really just a 2 sort of substance relationship, 1 reactant to 1 product, 1 reactant to 1 reactant, 1 product to 1 product. By the way, another very common thing that people get confused about is you could do these relationships wherever you need them, which means like this one, we went from the left-hand side of the arrow to the right-hand side of the arrow. On one of the first examples we did, we went from the right-hand side of the arrow to the left-hand side of the arrow. And by the way, you don't need to cross the arrow either. You could stay on the left-hand side and just do it between the 2 reactants. If you had 2 products like in this one, you could do a calculation between the 2 products. So sometimes people think you have to go across the arrow in terms of the relationship, and you don't. You just need to do it between 2 things in the balanced equation. Rather, they're reactants and products, reactants are reactants, and products are products. Question on that? All right, well, that's a good stopping point for right now.